Okay, now we will go to the second part, that is vectorization. You may heard NumPy vectorization before. That is, we have two arrays. The first is A, that is maybe 1, 2, 3, and the second is 6, 5, 6. That's 4, 5, 6. And it will multiply them. It will take the multiply operator at every position. That is the vectorization. We do not need for loop. And in the Numba, they are very same. We use the vectorized decorator to implement vectorization, and we need to import it from Numba. What we should do is only to put the decorator on our function, and we pass our array into our function. Every time we call the function, instead of the x is not actually the x is not the array. Actually, is every element in the array. So the x is actually the scalar. So what Numba do is more similar, like call this, then call this, instead of directly call the whole array. So this follows the original definition of vectorization. That is, we write a function that can be used to process scalar. It can be vectorized and to process the whole array. And we will compare the time benchmark with NumPy. We can find it is much more faster than the NumPy log. Also, the function can accept multiple keywords. And for every time we call the function, xy, as we mentioned, it is a scalar. So it is actually every element in the array. So the first element, when we compute the x is 1, then y is 4. The second time we call the function, that the x is 2, the y is 6, and so on. So you can't think that the x is an array and the y is an array, and we do the subtraction. No, it's actually xy both scalar. Okay, then we vectorize the scalar function into a array function, so we can get the final correct result. I mentioned that we can set the no Python equals to true in vectorize to ensure our code is executed in no Python version. In vectorized decorator is very useful, but it has a limitation that the input can only be considered as an array. There is a concrete example that not can be vectorized by the vectorized decorator, but it also is kind of vectorization that we call it generalized vectorization. That is, we have an array. The shape is 4 times 4, and the scalar that is of shape of 4. And we want to add every row. The first row we should add the first element in the scalar, and the second row we should add the second element in the scalar, and so on. And we can do this in NumPy by the broadcasting operation. If you are not familiar with broadcasting, please check the NumPy official document. It will show you what is broadcasting and why the shape is the same as the original array. So we can check actually We check the third line. The third line is numpy.arrange. So the third line is 8, 9, 10, 11. So the first element in third line is 8 plus 3, that is 11. The last is 11 plus 3, that is 14. And actually, we can do this with the general vectorize by using the GU vectorize. And you see there is some extra information in the GU vectorize. The first parameter is a list, and it gives us the input type in the of the function. That is, the first parameter we want to vectorize is a array with int 64 data type. And the second is a scalar. Actually, the scalar is 1, -2, 3, -4. And the result is the int 64, and it is array. And the second parameter is a string, which tells us the specific shape of our array. We pass an array of n and a scalar, then we will get an array of shape of n. This is the result. So the hyphen and larger. So the this combined operator means what we will get the shape of the results. What we will get in the results shape. And we mentioned that there is some different compared to the vectorized decorator. There is the third. We have the third keyword, that is our result, and we need to write our computational result into the last parameter. And if it is an array, we have to use the slice instead of assign the result to the last element itself. So that means we can't write a code that is results equals to array scalar. This is wrong, because when we use slice, that is we change the value of element. But if we use this, write like this, we will change the address of the array. That is different. So now we can find our array is a one-dimensional and of shape n, and our scalar is sorry, the scalar is a single element. Then we put our result into the result the last keyword variable. We can get the same result as what we expected before. There are some more complicated annotation which is more useful. For example, we can accept a two-dimensional array with data type of float 64, and the second is parameter is 64, also a two-dimension array with data type of 64, float 64, and our result is also the shape, but the shape is different. This is more like a matrix matrix multiply. So A at B equals C. Just the at is the matrix or multiply or operator in NumPy. So we have a matrix of m times n, and the second is n times p, then we'll get an array that is m times p. And also, We find that the second example, the first parameter is in a single scalar. The second is a float 64 array. And the last is our integer array. And of course, this is two-dimension array. So the shape is 1 and n, and it maps these two parameters into n times n matrix. So here is a more specific example, which the function input is array of an integer. Of course, this is a one-dimensional array. And the second parameter is the same. And the third parameter, that is float 64. This is our results. It also is an array. Okay, so what should we do? We are given a array A, and we want to normalize A according to B. So we want to map 10, 25, 22, 3, 6 into 5 to 10. And also want to map 1, 4, 5, 3 into negative 1 to 1. And this is exactly what the general vectorization do. So every time for example, in the first position, the A actually is 10, 22, 3, 6, and the B is 5, 10. They are both array of one-dimensional. So for every position of results, we need to write the normalized value of A into the results variable. Then finally, we can get the right results by calling the function and pass the A and B into the function. And then, and finally, we want to mention that if our return value is a scalar, because you see that the return value here is an array, and the return value here is they are all array. We just the example we just gave. If we want to return a scalar, so what we will do? So we have to annotate our results also as an array. This is very special, although this is scalar. And in the second parameter, we should also write the we just write the results dimension as a parenthesis, single parenthesis, without any shape. And if we want to save our results into the result variable, we need to use slice index. So we results index 1 equals to array.sum. So we save the variable into the scalar. Although this is actually a scalar, but we use the index. This is a special or some weird rule in Numba. So this is special. So what they just do? Actually, this is a row-wise sum. So the range 16 is a range 16. One, two, three, 0, 1, 2, 3, and we want to do the sum operation row-wise. So the first is 6, the second is 13 minus the 22. And also, every time we pass our array into the function, the array is a row. The row. So the first element is 0, 1, 2, 3. And the second time we call the function is 4, 5, 6, 7, and so on. And then finally, we can get the right results. So this is a note on what we should change when returning the scalar value.